Okay, so what do you think? Let's look at section 2. We're looking at the first law of thermodynamics. And the four strokes are intake, compression, and ignition, exhaust. Which work is done on the gas? Done on the gas. And in which is work done by the gas on the piston? Which ones are adiabatic? And which increase the internal energy of the gas? Which decrease the internal energy of the gas? And which transfers heat to the outside of the environment? So if we look at energy conservation, a frictionless roller coaster simply converts potential energy into kinetic energy and then kinetic energy into potential energy. A real roller coaster, we know, is not frictionless. There is friction, so we do lose some energy, and mechanical energy is not conserved because of that friction. So the track and the wheels have an increase in the internal energy, which we're going to symbolize by U. And here we can see when it's going up here, we have the highest potential energy. When we get to point C, where there's more kinetic energy, less potential energy, we're losing more energy, the U. Down at D, we're back to about the starting point, so we have mostly kinetic energy, no potential energy. We're getting more of that internal energy. And here again, we've lost a lot of energy, and it's in the form of U here. We'll watch this.
The total energy in a closed system is always conserved, although it may be converted into other forms. While this roller coaster car is being raised up, energy is being added to the car from an outside source. This is not a closed system. The potential energy gained is shown by the red bar on the graph. After the car is released from the top of the hill, we will assume that the only source of friction is at the axles of the roller coaster wheels. Since nothing is adding or taking away energy from the car, it can be considered a closed system for the rest of our example. As the cart goes down the hill, its potential energy is converted into kinetic energy. Kinetic energy is shown by the blue bar. Gradually, friction at the axles causes heating. This change in internal energy is shown by the green bar. By the end of the run, most of the mechanical energy has been converted into internal energy. At all times after the first hill, the total energy remains the same.
Okay, so that shows you in motion the different changes of energy there. So the first law of thermodynamics is that a change in a system's internal energy is equal to the energy transferred to or from the system as heat minus the energy transferred to or from the system as work. Now, we have to pay attention to signs because sometimes heat is positive or negative, work can be positive or negative also. So, heat is positive if energy is added to the system as heat, but Q or heat is negative if the energy is removed from the system as heat. If there's no transfer of energy, then Q is equal to 0. Same as W. Work is done by the system, so if a gas expands and moves out and does work on something else, that is a positive work. Negative work is when work is done on the system or a gas is compressed, something else is pushing down on that gas. Work is equal to 0 when there's no work done.
The first law of thermodynamics states that the change in internal energy in a system is equal to the energy transferred to or from the system as heat minus the work done on or by the system. Isovolumetric means same volume. Since the volume does not change, no work is done. If energy is added to the system as heat, the system's internal energy increases. If energy is removed from the system as heat, its internal energy decreases. Isothermal means same temperature. There can be no change in the internal energy of a system. The energy transferred to the system as heat may be removed as work done by the system, or the energy added to the system as work done on it may be removed from the system as heat. In an adiabatic process, there is no transfer of energy as heat. If work is done on the system, its internal energy increases, or if work is done by the system, its internal energy decreases. By definition, in an isolated system, there is no heat or work interaction with the surroundings. According to the first law of thermodynamics, there is no change in the internal energy of an isolated system.
Okay, so let's look at this practice problem. A gas is trapped in a small metal cylinder. Color pencil here. With a movable piston and is submerged in a large amount of ice water. The initial temperature of the gas is 0 degrees Celsius. A total of 1,200 joules of work is done on the gas by a force that slowly pushes the piston inward. With this process, the isothermal, adiabatic, or isovolumetric. Well, it's not isovolumetric because it's slowly pushing it inward. Okay, so delta V is not 0, so it's not isovolumetric. The isothermal is the change in temperature 0. Well, we know with the initial, let's look at adiabatic, means no energy is transferred. Work is done on the system, and it increases the system's internal energy. So what do you think it would be? It is isothermal because we are doing work on the system. The system is not changing any temperature. It's 0 degrees Celsius. So how much energy is transferred as heat between the gas and the ice water? 12,000 joules. There is 12,000 joules or 1,200 joules of work done. How much ice would melt as a result of this heat transfer? And 3.6 grams. Now you would need to use some of our equations from a previous chapter that we didn't go over, so we would not have to do anything dealing with the grams. Okay, heat engines. The process is cyclic, so the working fluid returns to its initial temperature and pressure. So the change in U is 0 because the beginning and the end is the same. Heat engines take heat from a substance at a high temperature, use that energy to do some work, and then expel the substance at a lower temperature. Internal combustion engines are heat engines. The hot gas do the work on the piston and then are expelled to a lower temperature environment. Here's a steam engine where we're adding heat to the heat engine. It's doing some work and it's releasing also the heat left over. So hot steam enters, does work on the piston, and now the colder air is exhausted or moved out. Refrigerators are opposite of heat engines. Heat moves from a lower temperature to a higher temperature. This does not violate the rule because the work is done and it moves heat in the opposite direction. And same with air conditioning systems. So they have cold, compressed air that goes through that will take the heat out of the outside, absorbs the heat, and it releases that heat then. So we watched this video in the first section. You can go back and rewatch these two videos about the refrigerator and the combustion engine. So which one is work done on the gas? That would probably be compression because it's going down onto the gas. And which work is work done by the gas on the piston? Well, when exhaust, when it expands again. Think about what's adiabatic, which is increasing the internal energy of the gas. decreasing the internal energy of the gas, and which transfers heat to the outside.